Okay, let's take a look, please, at something I got for you here. Okay, I want to look at continuation of what we talked about yesterday. Okay, yesterday we talked order of operations, recall. Order of operations, everything we did with order of operations. Oh, I think I messed something up already. Hang on. There we go. Okay, everything we did with order of operations yesterday revolved around PEMDAS. Right? We simplified stuff. We took, in class and on your homework, get a chance to work on this. We took jumbles of all kinds of numbers mixed together with division and subtraction and multiplication, etc. And we simplified it down to a single number, right? And to do that, we just started at the top and worked our way down the order of operations tree. And you know that well. Okay, what we're going to do today is something a little different, but it's strongly related. Now, when you want to do some algebra that's a little harder than simplifying, we want to do some solving. We're going to solve for x. And it doesn't have to be x, but we'll just make it x today. Solve for a variable. Or isolate x. You're doing the same thing. When we're solving for a variable, we're just isolating it on one side of an equation, right? Now, to do that, we are going to reverse the order of operations and go backwards. And this will always work. You're going to be able to do this next year in Algebra 2, even when we get to hard stuff like polynomials and quadratic equations and exponential functions, a bunch of and beyond that, when we go to trig stuff and pre-calculus, and even in calculus, when you're doing algebra, this will always be the way you do it. When you want to isolate a variable, you just reverse the order of operations, and it gives you a recipe for what steps you do first and second and third, etc. Now, when we're going to isolate a variable x, though, and I'm going to kind of lay this all out on the line here at first, and we'll go back and look at it more slowly with some examples. That means, or implies, that you've got to be able to point at a certain x to isolate, right? And so there will be some cases, and we'll see a couple today, where we get an equation that has more than one x in it. And in that case, we've got to make that simpler. We've got to work down this side of the order of operations direction until we get a single x that we can point at, and then we can isolate it by working backwards through the order of operations. Okay? So that's kind of our plan. If that didn't make perfect sense, do not panic. It will by the end here, I promise you. Let's start off at the very beginning here. What's an equation? Well, an equation is just a statement in which two expressions are set equal to each other. Nothing more, nothing less. So out of those four examples up there, which of them are equations? A and D. Right? No big deal. We can see equal signs in both of those. So A and D. Now, do you see any, what are the other two called? Expressions. Yeah. These are expressions. So what does an expression mean? It's just a bunch of algebra stuff put together, numbers and variables, without an equal sign. Can anybody see another expression up there that I haven't circled? Say it again?
3x.
Yeah, there's one. 3x minus 7 is an expression, right? It's part of the equation, but it's just an expression. Even 12 is an expression. That's a number. Numbers and variables put together make expressions. Add an equal sign, and it's an equation. Okay, make sense? It's good to get all this terminology straight. I can remember being in a math class in high school and having heard all these terms thrown around and being at a point where I didn't really understand exactly what they all meant. And now, and I want you to. I want you to know what all those things are. Okay, the properties of equality. We'll quickly go through this because this is stuff you all also already know. And we're going to boil all this stuff down to a real simple idea. That's just how you approach solving equations. The addition property of equality sounds fancy, sounds like it's all very math-like. says that you can add the same term to both sides of an equation. The subtraction property of equality just says you can subtract the same term from both sides of an equation. And we're going to get a couple others there. But one thing I want to point out while we're on the subject here is this word term. What does the word term mean? In math, I suppose. What do you do with terms? We use that. You'll see that word in books, and you'll hear people talk about terms in math, and I want you to know what it means. Very simple. A term is just anything in math that you add or subtract. We call a term. Things that are added or subtracted are terms. Nothing more, nothing less. That's it. We have two other properties. You might guess what they are. The multiplication property of equality and the division property of equality. And they both just say you can either multiply both sides of an equation or divide both sides of an equation by the same wrong word. That's not the word that should be there. I borrowed this PowerPoint, and they made a mistake. It shouldn't say term. It should instead say what? Does anybody know? What do you call things that are being multiplied or divided? Things, yeah. More specifically, factors. Very good. We could call them yeah, I will. I'll edit it and re-up it for you, so it'll be correct. But that should say factor. Now, all this stuff boils down, though, to a very simple idea. Notice that it says you can do the same thing to both sides. Add, subtract, multiply, or divide. So, bottom line, if we have an equation, we have to treat both sides equally. You have to, what you do to one side of an equation, you have to also do to the other. You have to treat them equally. And you probably already knew that, right? Okay, let's look at a couple examples. Now, to solve an equation for a variable, we already said that we're going to do the order of operations backwards to isolate. And we're just going to keep on going, keep on moving through the steps, that we take when we reverse the order of operations until we isolate a variable, get it by itself on one side of the equation. But sometimes, before we can start doing that, if we cannot point to a single variable to isolate, we have to simplify it to begin with. So we might have to make things simpler before we can actually start solving. Let's take this one for an example. Nobody's saying anything yet. Everybody just take a look at that for a second. Can you point at a single x there? I can. Right there, right? There's a single x. So we want to get that by itself. To get it by itself, all we have to do is just reverse order of operations. So what's the first thing that we might need to do? Add or subtract. So to get that x by itself, to get it all by itself on the left side, I've got to peel everything away from the left side and move it to the right. First step. Subtract 8. Yeah, good. We'll subtract 8. Okay, and if I subtract 8, it goes away from the left side. 16 minus 8 is 8. Very good. Okay, check that off. First step is done. Now what? Okay, good. I've really got a choice here, don't I? I could either divide both sides by 2/9, or better than that, I could multiply by 9/2. We never really want to divide by a fraction. We'd rather multiply by the reciprocal, right? So, what happens if we do that? Let's take a look at this. If I multiply both sides through by 9/2, how do we do that? Take a second and think about that. I need a drink of water. Ugh. Ah, good. Okay. When we're multiplying a number by a fraction, typically the easiest way to think about that is to write the number as a fraction. Let's make that an 8/1, how about? Okay, now.
Oh, and then you cross.
Good.
You cross. Multiply.
Cross reduce or cross cancel.
Cross cancel.
Very good. Okay.
4 and 2, 1.
Excellent, excellent.
Yep.
If we multiply fractions, now we can multiply fractions straight across, but if I do that, and it's not terrible, but watch what happens. 8 times 9 is 72. 1 times 2 is 2. Well, that's pretty big. 72 over 2, we got to think about doing division with big numbers. What is that equal to?
36.
36, but you got to think about it a little bit, don't you? And it could have been worse, right? The suggestion is, and it's a very good suggestion. Now, let me say this very clearly, because this is a common mistake people make in math. You can only cross-reduce or cross-cancel fractions if you're multiplying, not adding, not subtracting. Right? It doesn't work for those, or dividing, only for multiplying. So in this case, 8 over 2 reduces to what? 4 over 1, and now we're done. If I multiply straight across, I get 36 over 1, and dividing something by 1 doesn't change it, right? So it makes it easier. So it's always easier, if you can, to cross-reduce and then multiply. Okay, so. And we got an answer of 36. How do we know if it's right?
Substitute the x for 36.
Good. Okay, we can go back to the original equation, and we can substitute that 36 in for the variable x. And what's going to happen if we did it correctly? Good. It's going to make the equation true. Now, in math, we call that satisfying the equation, satisfy the equation. But what it means is it's going to make that equation work, right? That's the one value of x that makes this equation work. So how many solutions are there this time? One. That's it. It's 36. Okay? Yikes. What about that? What's different about this one? 3 x's. Okay, so I cannot point at a single x up there and isolate it. I've got to make this simpler first. How do I do that?
You combine them.
Yes, ma'am.
You have to use the distributive problem.
Good. Good, good. Okay, we're going to distribute the 5, it looks like. What's the other number? What's the other number that gets distributed?
Negative 4.
-4. So we got to distribute the negative sign also. Good. What do we get if we distribute the 5? 5x. Good. Good. Okay, good, good. All right, we're on the right track here. Okay, very good. Okay, what's next?
You combine the x's.
Okay, I can combine like terms, can't I? Now, let's break this up into pieces. And this isn't a bad idea. Later on, as you get better and better at algebra, you're going to be able to do more and more mental math and skip more steps. But for now, let's not do that. We'll get there soon. When we face a situation like this, let's just try to get each side of the equation simplified. Now, the left side is already done, isn't it? Nothing I can do there. I can't combine 5x and -10. Those are different kinds of terms. But on the right side, I've got 2x terms. -8x plus x becomes what?
Negative 7x.
-7x. Okay. Now, here's another issue we got to deal with. There are multiple ways to do this problem. And I'm not going to say that there's only one way, but I am going to say there's one way that's probably easiest and maybe even best. It's a popular thing to say is, well, everyone does stuff their own way. Let them do it their own way. That doesn't really work in math very well. When you go far enough in math, like, for example, in calculus, in the calculus class I teach, I'm going to say that probably 75 to 80% of what I do in that class, and what students do, is not just try to get the right answer. It's try to get the right answer the correct way, the easiest way. Because the further you go in math, the more horrible things become if you don't do things the best way. So we always want to be in that practice in math of doing things efficiently and easily. Now, this is a relatively minor point, but it is a point. Which direction should I pull the x's? Should I push them to the left or push them to the right if I want to isolate x? To the left. How come? Yeah, I'll get a positive number of x's. Good. And that's going to make life easier for me later on in this problem. So as a rule, we always want to gather the variables where I have the most of them to start with, right? So we'll add 7x to both sides. It's going to give us our 12x, right? And now, finally, I can point to a single x, and so I can isolate it. Okay, now don't say anything out loud. Everybody look at that and see if you can identify in order what are the 2 steps I would take to get the x by itself. What am I going to do first? Add 10. Good. Okay, what next? Divide by 12. And am I done? Is that good?
No.
Not quite. I can reduce that. I can. What number goes into both 12 and 18? 6. Goes into 18 3 times and 12 2 times, so negative 3/2 is our final answer. Good. One solution to that one also, right? That's the only value of x that makes this original equation work. Okay? All right, now I'm going to give you a really ugly looking one. Yikes. That looks bad. That looks terrible because it has so many fractions in it. How many people like to add and subtract fractions and multiply and divide fractions? You'd be lying if you say, wouldn't it be easier just to deal with the integers? Fractions make things harder, right? And there's a lot of fraction work there. If I want to get this x by itself, I'm going to have to subtract 2/3 x to this side, add 3/10 to that side, divide by some fractional coefficient both sides. That's a lot of stuff with fractions. Wouldn't it be great if we could just get rid of those fractions and trade it for a better problem? Wouldn't that be awesome? Okay, decimals, that's one way to do it, but it's not the best. It's not bad, but it's not the best. The reason it's not the best is because not all decimals terminate. 1/5 works great, that's 0.2. 3/10 works great, that's 0.3. But what about 2/3? Well, that's 0.66666 forever. Anytime you stop it, you're rounding it, and you're actually changing it to something different. And so it's not ideal. There is an easier way to do this, and a better way to do this. But there is a way we can do it. We can trade this ugly problem. We can trade it in for a better looking, simpler problem. And the trick that we do is called clearing the fractions. Any suggestions how I can do that? Just remember doing something like this? Did you learn this trick? It's a great trick. Okay, all you do, when you're going to clear the fractions out of an equation, here's what you do. You look at all of the denominators in the entire equation. What are they? 3, 5, and 10. And we're just going to build the least common multiple from those denominators, meaning the smallest number that they all divide into. 30. Good. 30. So then we're just going to multiply both sides by 30. Now I want to show this to you two ways because I want to show you an even better trick, well, an additional trick that makes this very simple. If I just go through this process of distributing 30 to both sides, it looks like this, doesn't it? If I distribute the 30 to the first term, I get 30 over 1 times 2 over 3x, right? Distribute it to the next term, and I get plus 30 over 1 times 1 over 5, 1/5 x, right? Equals, on the other side, 30 times 2x, that's no big deal. That one we can do.
There's no x in one.
Oh, whoops, you're right. Sorry, my mistake. No x. Thank you. And then last term, minus 30 over 1 times 3/10, right? Now, what do you notice about all of those fractions that we're multiplying? Do they reduce? They do, don't they? Yeah, look at that. 30 over 3, 3 goes into 30 perfectly. What's that reduced to? 10 over 1. What about here? 30 over 5? 6 over 1. 30 over 10? 3 over 1. Look at that. That's great. We get 1s on the bottom of all of those products of fractions, right? Is that an accident? What do you think?
How come you put the 30 on the top instead of the bottom so it's number?
Okay, 30, good question. 30 is just a number that I built from the denominators. But what I'm going to do is I'm going to multiply both sides of the equation by 30. So I'm actually multiplying by 30 over 1. Good question. It came from the denominators, but it's just a new number built from the denominators that I multiply both sides by. Make sense?
Yeah.
Okay, so now look what happened here. I got 1s on the bottom of all of these. So this first term just becomes 10 times 2 is 20x, right? Second term becomes 6 times 1 over 1 is 6. 30 times 2 is what? 60. And then the last one, I get 1s on the bottom, and 3 times 3 is 9. Now, is that an accident? Did that work out so well? Does that surprise you? It is, even better. No, it doesn't. No, you might. But it shouldn't surprise you, because think how we built that 30. I asked you the question, what's the smallest number that 3 and 5 and 10, the denominators, all divide into? So of course that's going to happen, isn't it? We kind of could have guessed in a way that was going to happen, right? Because that's why we built the number 30. We didn't just pick a number out of the sky. We picked 30 for a reason. And so we knew it was going to work out well. Now I want to show you a little trick how we can do this without having to write down all this stuff. This is really good, seriously. If you can get this, this will save you lots of time and effort. Okay, let's go back and try this one more time. I'm going to distribute to 30. To both sides. Now watch what we can do. We already know in advance that we picked 30 because all those denominators divide evenly into it. So every time we distribute the 30 to a fraction, we already know it's going to reduce. So here's what we do. 30 over 3 is what? 10. So 10 is the number that we multiply by the numerator. 10 times 2 is 20. We're done with that first term. How about that? That's good, right? 30 over 5 is 6 times 1 is 6. It's pretty bad 20. Equals 30 times 2x, and 30 over 10 is 3 times 3 gives us minus 9. Isn't that great? That is a lot easier, right? So when you're distributing or you're clearing fractions like that, as you go through, just always go through the process of dividing the denominator by that number to figure out what the reduced number is that you multiply by the top, right? Okay, that'll save you lots of time. All right, so we get that thing down to here. Now what? Got to simplify. Okay, I've got x's in two places. Where am I going to push my x's?
Right.
To the right. Good. I'll subtract 20x from both sides. What am I going to be left with on the left side of the equation then?
6.
Just a plain old 6. The 20 is going to go away. What about over here?
40x minus 9.
Good. 60x minus 20x is 40x minus 9. Now I've got it down to where I've got a single x that I can isolate. So what do I do to isolate it?
You
Add 9. Good, good. So 40x equals, the 9's gone. What's on the other side now?
15.
15. And then I got to get rid of that 40, push it to the other side. How do I do that? Divide by 40. Okay. Hey, let me have iPods and stuff put away, please. When we're in here, I want those put away. So divide both sides by 40. It gets rid of the 40 on that side, and I got my answer. X equals 15 40ths. That's correct. Can I reduce it?
No.
Is there a number that goes into 15 and 40? 5 does. How do I know that 5 goes into, really quickly, how do I know that 5 goes into both 15 and 40? Okay, because these numbers end in 5 and 0, don't they? Any number that ends in 5 or 0 is divisible by 5, right? Okay? So then 5 goes into 15, 3 times into 40, 8 times. We got it. Okay, last example. We're done. You're ready to go. Okay, what about this one? This is going to be a weird one. What do I do there? Distribute. If I distribute the 5, I get what? 20 or 5x minus 20? Now, what happens here? If I subtract 5x from both sides, what? They cancel. Look what I get for an answer. Negative 20 equals 12. Is that ever true? No, that can never be true. So, you suppose, how many values of x do you suppose are going to work in that equation? You say, none. 0. That's how we interpret that. If we get a nonsense answer like that, that's not true, that's never true, then that means there are no values of x that work. There's no solution. Okay, now look at this other example that's sort of like that. If I combine like terms, 7x minus 3x is 4x plus 14 equals 4x plus 14. Well, what if I subtract 4x from both sides? I get 14 equals 14. That's always true, right?
Yep.
If I subtract 14 from both sides, I can do that. If I subtract 14 from both sides, though, I just get 0 equals 0. That's also always true. If I get an answer that's always true, how many values of x do you suppose are going to work? All of them. Doesn't matter. Every value of x. All real numbers. There are an infinite number of answers. Infinitely many. Okay? Make sense? Is that ringing a bell? Okay. Alrighty. Let's